Hello everyone. Due to overwhelming response to the physics practical and requests from students, I decided to do a video on the skills required for the physics practical and the relevant topics that the student or candidate should prepare himself or herself for the paper 3 physics practical. Okay, so my focus will be on the important skills in analysis, conclusion, evaluation, and some tips in doing experiment planning in the physics paper 3 practical. So according to the syllabus outcomes, candidates should be able to analyze and interpret data or observations appropriately in relation to the task. So the candidates will be assessed on their ability to present data in table form or graphical form. And students or candidates will be required to read off values from a graph directly. In doing so, they should know how to draw dotted perpendicular lines to connect the data points to both the horizontal and the vertical axis. So when you are asked to, let's say, determine, okay, a point on your graph, you are supposed to do this. Okay, on your graph, you have to show the dotted lines linking to the vertical and the horizontal axis. Okay, both has to be shown in order to show the examiner that you know how to get the value and not just leave it up from the graph casually. Okay, data value should be read to the accuracy of half of one of the smallest square on the grid. So if this is the square on the graph, 1, 2, let's say, you can read up to 1.5 if the data point is as such. Okay, now in physics practical, candidates may be required to determine gradient. So these are some of the important precautions to determine the gradient accurately. Number 1, choose 2 points that are far away, minimally across half the length of the best fit line. So let's say this is the best fit line, right? You are not supposed to choose 2 points here, which are so close to each other. It should be more than half the length. Okay, or even half, but for me, I will take the 2 extreme points, but do not choose the points from your data table. Okay, try to use the points on the line, but not on the original data point you use in plotting a graph. Okay, the purpose of choosing 2 points that are far apart, so this is the rationale. Okay, the reason is this helps to reduce the percentage uncertainty. It helps to reduce margin of error when you calculate gradient. Okay, now draw a right angle triangle on the graph when determining the gradient with these 2 chosen points. Calculate gradient using the formula that you learned in eMath, y2 minus y1 over x2 minus x1. Okay, gradients itself do not have units and should be recorded in either 2 or 3 significant figures. However, if the gradient is subsequently used to represent a physical quantity, for example, this gradient could represent gravitational field strength, okay, which can be either Newton per kg or meter per second square, then you must take note of the unit. You do not need to write the unit for the gradient here, but when you use this value in the subsequent question, then you need to consider the unit. Okay, now, so this is the points that we have mentioned. Next, in a question, you may be asked to find the intercept, either the x or the y intercept. Okay, so please read the intercept directly if possible. Or you can also do this. If let's say, right, the graph look like this. Okay, so you can't really see where's the y-intercept because this is your graph paper. It doesn't extend all the way to the negative portion of the vertical axis. So in this case, you have to do this. Substitute the value of the gradient and coordinates of one point using the y equal to mx plus c formula. Do you recall that in your E-Math, you learned that? So if you recall this formula, the formula used to represent a straight line or equation rather. So you need to find the y-intercept, which is c. You substitute any value, y and x, and use the gradient we calculated earlier to work out the intercept. Okay, if you have anonymous result, how do you deal with it? When the graph is plotted and there are points that are far away from the graph, for example, you have a graph that looks like this, but you have an anonymous result, anonymy, okay? Either you circle it and say anonymous point directly on the graph if you do not have enough time, or just ignore this when deciding on your line or best fit. So you must acknowledge this as an anonymous point, number one. And when you determine your best fit line, you don't consider it as part of the line. However, if there is enough time, if time permits, you should consider repeating the experiment for this particular result to verify the reliability. Sometimes you may carry out the experiment wrongly and obtain inaccurate result. So you need to double check again so you can avoid this situation because there could be marks deducted for accuracy. Okay, now drawing conclusion from the interpretation of experiment data or observations and underlying principles. So the relationship between the independent and dependent variable can be derived from the graph to draw conclusion. Hence, if a graph shows a straight line, the dependent variable is linearly related to independent variable. So this is how you should describe the trend of the graph. Okay, the dependent variable, for example, it could be temperature, represented by capital T, is linearly related to independent variable. So the graph may not cut through the origin, so it looks like this. So this is what I meant, linearly related. Okay, so choose the right phrasing. But if the graph cuts through the origin, meaning not all the graph must start from origin. Let me emphasize on this. Many students force their point through the origin. No. Okay, it depends on the experiment data you obtain during your experiment. And you need not start from zero if the data doesn't allow. We need you to spread out the graph such that the graph covers at least 3/4 of the space given. Okay, so if you squeeze everything, I have a student who draw like this. By right, it should be like this. So this shows bad graph drawing. Okay, you did not maximize the space, and by doing this, you create a high percentage uncertainty. So this is low percentage uncertainty. This is high percentage uncertainty. Okay, now go back to this, right? If the graph cut through the origin and it is a straight line graph, you describe the dependent variable as directly proportional to the independent variable. Okay, if the graph shows a positive gradient, you can describe the graph as the independent variable increases. So as the x-axis, which is the independent variable increases, dependent variable increases non-linearly, or better still, if the graph look like this, like what I shown, you say dependent variable could be temperature or could be other variable like maybe speed, I don't know, increases with increasing rate or increases at an increasing rate also can. If it's something like this, right, you say this variable, the dependent variable is increases at a decreasing rate. So for this graph, on the left-hand side, you say maybe this is the y-axis. You will say maybe t as maybe x increase, y increases at increasing rate. Okay, this is a more accurate, more detailed description of the trend of the graph. For this one, it says as x increases, y increases at a decreasing rate. Okay, use this term in your answer, okay, for both theory and as well as the practical. Okay, so this description is for this type of graph. This one is for this one. Okay, so this is how you describe the graph. Okay, now there will be questions that require you to make predictions based on the data and conclusion. So there could be modification introduced to the experiment, and students are required to predict the experiment that will need to be changed. For example, after the graph of sine I against sine R is plotted, I and R are the angle of incident and reflection respectively. It should be refraction. There's a typo there. Okay, refraction. Student may be asked to predict how the graph will change if a median of a higher refractive index is being used. This is a very popular question. So you have, let's say, n equals to sine I over sine R. Sine I over sine R. Okay, you should be very familiar with this equation by now. If you're in set 4, this is a topic covered in set 3 under the topic of light, refraction of light. Okay, so when they say that, okay, let's say I change the median to another one with a higher refractive index, how will that change the graph? So if the graph shows sine against sine R, so if this increase, you expect this n is the gradient of the graph. So you expect the gradient to increase. Okay, so the graph will look steeper. So maybe from here with a higher refractive index, it will become it will still be a straight line, but with different gradient, a higher gradient because the n is higher, something like that. So you need to demonstrate some conceptual understanding and predict what will happen if they change the scenario. This type of question is very common, okay, and will be asked. And of course, the question that will always be asked in all practical is significant source of error. So later I will show you a table where it summarizes the different possible source of error for different type of experiment and how to explain the effect of this error and suggestion how you can reduce the error according to point 5. And how do you improve the procedure by either reduce or totally overcome the error. Okay, now, so to identify where errors may be introduced, students should consider number 1, which procedure in the whole experiment is the difficult part to carry out. For example, during the experiment, the student realized that the meter ruler is required to be clamped horizontally. So it's very difficult to ensure that the ruler is set out horizontally. So you could actually list it as one of the source of error by saying that, hey, the ruler is not clamped horizontally. So to improve the experiment, maybe you can put a set square to adjust the position of the meter ruler such that it is more horizontally aligned. Next, which measurement were difficult to observe and record accurately? If the experiment involved measuring time, good, because there's always this issue about human reaction error. But please, students, don't write human reaction error. You're not going to score any mark for writing that. You have to be specific how the time is causing the error. So experiment requires students to record time, for example, observing temperature reading at different time. So you can say that, while taking the reading on the thermometer, there's a time lapse between reading a thermometer and stopping the stopwatch. Okay, that will lead to inaccurate result. Time lapse means you cannot ensure that the time where you stop the stopwatch is the same time where the reading was taken. Okay, now next thing is think about, okay, so other than procedure, measurements, you can also think about control variable. Like, think about these 3 questions in order to help you determine the significant source of error. So the last one is control variable. So think about the control variable that cannot be kept constant. For example, in the experiment on electricity, right, the resistant wire may not be taut or straight or got nicks that result in inaccurate measurement of the length of the wire. So the resistant wire itself may be a problem itself because it's supposed to be straightened. But when it's not straightened, then the length measure will not be accurate. And you know that it's impossible to straighten it because there is needs that it causes inaccurate measurement. So in summary, I'm not going to go through every single one. So if you're interested, right, you have to get this from me personally. Okay, I will give you the copy of this document so that you can use it for your benefit. So I try to summarize everything based on the type of experiment that one may encounter in a practical exam. So these are all the source of error and the suggested improvement. Of course, there may not be improvement for every error. Okay, so try to choose something that is that have improvement and error for remembering. But of course, you cannot just blindly memorize this because the nature of the exact experiment may be different. So you have to see whether the experiment, for example, involve wire. If it doesn't involve wire, then you cannot use this, right? So you have to be very careful at what you are choosing. But most of it should be here based on past year papers. Okay. For example, the wire may become hot after some time. So changing the resistance. So when the wire become hot, right, it will affect the resistance of the wire. And then when the resistance changes, I and V are also affected. So maybe one advice is to why not we carry out at a higher voltage or lower current to minimize the heating effect of the wire. Okay, because wire is often used in the electrical experiment. You definitely need wire, and this could be one of the significant source of error to consider. Then you can also talk about other more more prevalent one, like the needs on the wire, which I mentioned earlier, leading to inaccurate measurement of the length. That means that you can improve it by using wires that are perfectly straight and no need. But this one is very hard to achieve. It's just a suggestion. But to be very honest, it's not possible to do this. But you can suggest it, like, can improve the wire by ensuring there's lesser needs. But it can't be perfectly straight. Let's be very truthful about it. Okay, and also if let's say the experiment involves you using jocket, okay, to make contact point, you can also talk about the contact is not consistent, causing variation in the reading of V. So ensure that the jocket is placed perpendicularly to have consistency. So there are other types of experiment, like spring experiment is very popular also, under the topic on forces and maybe moment. Here are some of the suggestions. YouTube experiment, or where you talk about maybe pressure, moment, horizontal ruler, etc. And glass block, mirror, lenses are all on the topic of light, quite a lot. Can just refer to it. Rolling pin, oscillation experiment, thermal experiment, getting more and more popular, this type of experiment. Let me know in case it came out. Now, so it's important to take note of the units. The next thing I want to go through is the common quantity that will appear in your practical, like length, time, mass, volume, stability, and even temperature. So these are the instruments that can use, and make sure that you are very careful in getting the correct precision of each instrument. For example, thermometer is to 1 decimal place. Yep. And so on. Just take note of that. For stopwatch in physics, just convert to 1 decimal place also. Yeah. Although the stopwatch reading is to 2 decimal place, but because we want to minimize human reaction error, because there'll be time lapse. So for physics is 1 decimal place, like 20.1. If it's the stopwatch read 20.12, right? You read 20.1. Clear? Okay. And then some precautions of experiment that to consider. This is very good. This is the precision of the instrument. I will not go through every single one. By right, you should be familiar by now. Okay? Yep. Like digital stopwatch normally is 1 decimal place. Yes, the one in your lab, the one for exam, normally is this. Meter ruler or even half meter ruler is to 1 decimal place for cm, but no decimal place for mm. Okay? Micrometer screw gauge, in case it come out, is 2 decimal place for mm. For vernier caliper is 2 decimal place for cm, 1 decimal place for mm. Measuring cylinder is depending on the one they give you, because measuring cylinder have different capacity, different sizes. So the you have to look at the division, the half. Take the take half the smallest division to determine the precision. Most of it will be 1 decimal place. Yeah, most of it. Then you have, but some of it is just whole number. Yeah, really. Some is whole number, some is 1 decimal place. So be careful about that. Thermometer I already mentioned. Electronic balance. It depends on the one the school gave. So there are 2 types. I'm not sure what your school has. It can be in 1 decimal place or 2 decimal place, but I'm sure it's not 3 decimal. The 3 decimal places is not used by student. Okay. The normal stopwatch is digital stopwatch. Some is 2 decimal place, but the one they give you should be 1 decimal place. Mostly. Yeah, I think so. Yeah. Then, no, sorry, I mean that they may give you 2 decimal places, but you read 1 decimal place in your exam. I mean, yeah, some could be just 1 decimal place. I'm not too sure about that. Yeah, it depends on what are the digital stopwatch they have in the school. So the uncertainty of the instrument is helping you determine, right, the number of decimal place you should give. So if you record the data in your table, right, if it's measured by the same instrument, by right, they should have the same decimal place. For example, if you use the stopwatch to measure time 1 as 20.1, then the next one 25.4, the 25.4 must be in the same decimal place at 20.1. Okay, milliammeter, yes, it will be used. So you have to take note of the precision. It's about 1 milliampere for the uncertainty. Ammeter and voltmeter is 2 decimal places. Just that for voltmeter, right, is the second decimal place is either 5 or 0 only. Normally, ammeter, depending, you must look at what they give you. So I'm putting down the range here for your reference. Projector is whole number. Take note of that. Spring balance is 2 decimal places normally. Okay, I'm not going to go through the exercises, but basically, these are how it looks like. Okay, yeah, for some of the questions. Then we move on to presentation of data. So what do you mean by a good table? So the independent variable should always be in the leftmost column of the table, with the subsequent column showing the dependent variable and the derived quantity, meaning the calculated value. And normally for the graph, right, you will use the calculated value as one of the axes, not the dependent or not the dependent variable normally. So the quantitative data recorded for independent variable must be in ascending order, and the heading of each column must include both the quantity and the units. The unit should be written in Solidus notation. Example, the length of the string is written as L/cm. Only slash you accept for physics. Same for other quantities. The body cannot include a unit. So your unit only shown in the first row. That's it, in the heading. Okay. Now, let's say for this question, right, they ask for change in length, right? You better put plus or minus here, my advice. Okay. Unless they say decrease in length, then you need not include the sign. But for this, you better write. Then the rest, you can see that because the length of the potato strip is using the same instrument, the same meter ruler is to 1 cm, right? 1 decimal place cm. So everything must be in 1 decimal place, even though it is 0. You still have to put the 0.0. So when multiplication or divisions are involved, the calculated value should follow the least precise significant figure, minimally to 2 seed. Okay, for plus and minus and average, it should be following the least precise decimal place. Very important. Okay, some people are very confused about this. Okay, I need to make it very clear to you. All right. Okay. So the measured data should be recorded to the resolution of the instrument. So the instrument show, let's say, 2 decimal places for voltmeter, you better put 2 decimal. If the instrument show 2 decimal places for the ammeter reading, you better write the 2 decimal place. Length is using a meter ruler, 1 decimal place for cm, right? Then you better put 1 decimal place, even though it's 0.0, you have to write it down. Okay, must. If not, there will be marks deducted. Then resistance. The resistance is a calculated value by taking V divided by I, correct? So it's obtained by the division of V and I. Therefore, the answer, so it is not a dependent variable here. It is a calculated data. So the calculated data should follow the precision. So the calculated data should not have a higher degree of precision than the raw data. So if the raw data shows 2 significant, your calculated data should also be 2 significant. So between V and I, right, the highest is 3 seed, the lowest is 2 seed. So this must be in 2 seed. Therefore, you see that for 11, 14, 16, it's 0.0. It's all 2 seed. Be very careful about that. Okay? Then for this resistivity, right, where you take the resistance, multiply by the length, okay, 4 times 5 is following 2 significant. So this here will be 2 seed, 2 seed, everything 2 seed here. Clear? Okay. So although this one, right, is 1.75, 20, right, you take this times this, you should get 320, not 320 point something. Okay. This is 3 seed, but this is still, but because, right, you want to make it consistent, so everything 2 seed will be good. Yeah. Here, you can downgrade to 2 seed, but you cannot upgrade your significant figure. That's my advice. So let's say this is 3 seed. This is this is 2 seed. So you follow 2 seed. What I'm saying here that you cannot upgrade. You can downgrade if you need to, but normally you just follow the significant. That is the safest. For example, 20, 3 seed. This is 2 seed here. This one times this one will be the answer will be a 2 seed, not a 3 seed. Okay. Now, when there's a division of a constant in the calculation of mean, the precision of the calculated value should not be more precise. Meaning, if you take, the average here, the time average for the oscillation is following the decimal places. But so this is actually 4 seed, correct? Then you'll ask me, how come here the period is 3 seed? The precision of the calculated data should follow the precision of the raw data. Okay, so when you take T average divided by 20, right? Okay, it should be downgraded to 3 seed and not keep as 4 seed. Meaning, why? Why is it not? You know why? Because this is 2 decimal place. So although this is 4 seed, this should not be 4 seed, because if this is 4 seed, the precision will exceed this. So just be very clear that you should not have the period, right, calculated with a higher precision than this. In terms, I mean, the decimal place should not be more lah. Because here the decimal place is only 2 for the T average. So your period should also follow 2 decimal place. Cannot go beyond that. Okay, then for T square, you just follow the significant figure, 3 seed, consistent. Use of standard form heading for very large. Yes, this is a very good practice. Please do this because we don't want you to show like very, very big or very, very small number. It looks very unglam on the table. It's not neat. It's not organized. You may be penalized. Okay, so don't do that. And it's also helping you to see the value clearer. So if it's a very big value like this, L over A, times 10 to the power 6, then you have to try to actually convert to standard form. Okay, so that we can also see the significant figure more closely lah. 3 seed, you know what I mean? Yeah. Now, here are some of the advices for graph plotting. Like you may or may not have title, but it will be better to have title so that you're very clear what is your y and x axis. More advisable to have a title. Then, for example, you can write a title as graph of temperature. Then in your title, right, you must not just say the quantity. You must say the symbol that represents the quantity, T/degree Celsius against time, comma, T/seconds, something like that. Okay? And it's always appearing on the top center of the graph paper. Okay? Then you must have access, proper label with quantity and unit. Okay? Horizontal axis must include the unit also, okay? Vertical axis and correct labeling of origin, if there is. Scale, the scale of the axis should allow majority of the graph paper at least 50% or even more. That will be better. For me, my rule is 3/4. Okay, but I know some teachers just say more than half. To make it say 3/4 and above. If you can use up the whole graph paper, that will be the best scenario. Try not to use odd scale like multiple or 3 lah. Try to have like nicer scale like 2 cm of graph paper representing 1 or 2 or 5 units, okay, in ascending order. Yeah. Minimum every big square, which is about 2 cm, need a numeral marking. Cannot have a big gap lah. Cannot like that. Then let's say this is 1. Then you have a very big gap, then 2. No, don't do that. Don't do that. Try to have minimum every big square. You have a marking there, maybe 1.5. You know what I mean? Yeah, try to not leave a gap. Don't do that. Need not start at 0. Need not. Okay. Ensure all the points are correctly plotted with a small cross. Nothing deviate from there. Okay. Each data point should be plotted to accuracy within 1/2 of the smallest square on the grid. Okay. All data values, including the coordinates on the line drawn and intersect, should also be read to accuracy within 1/2 of the smallest square on the grid. Okay. Best fit line. The line or best fit, which may be a curve sometimes. So best fit doesn't mean must be straight line. Wrong. It can be a curve. So it depends on your data point trend. You have to read your data point to see whether it look like a curve or it look like a straight line. The question may not tell you. Sometimes they may tell you, but sometimes they may not. Or you can interpret by the quantity they give you. Like for example, you know V against I, then for let's say they say that it's a resistor that obeys Ohm's law. Then you know that it's a straight line. But if let's say they are giving you like say filament lamp, you know that it doesn't obey Ohm's law. It's not an ohmic conductor. Then the graph should be a curve and not a straight line. So you really need to exhibit some of your concepts when you decide between a straight line or a curve. Okay. Then for the best fit line, right, it should have equal number of points on either side of the line over its entire length. A good line usually do not have points that seem to lie all above, like something like that. You cannot have all your lines are above the graph lah. It's very impossible. Okay, or be all below the line. It should be a good spread, a good average. What is the best fit line? A best fit line means good average. That is the meaning of best fit line, a good average. Okay. Okay. You do not need to cut through every point. There's no need to do so. Okay. Don't force it. Okay. Because there's always inaccuracy. Remember, there's significant source of error. So your value will not be exactly the same. Of course, you cannot be too inaccurate from the model answer, but there will be some discrepancy. Okay. And it's allowed. And you will not be penalized for accuracy. Basically, your trend is more important, okay, to get the mark than the actual result. Okay, I repeat, the trend is much more important than the actual result. The line drawn must be smooth and facilitate accurate reading of coordinates, because you will need to actually read the value from your graph that you draw. Students are encouraged to use a transparent ruler when drawing the line of best fit, so that they can see the other points through the ruler. So I will encourage you to use ruler that's transparent, okay? Not the metal ruler, transparent ruler. So that when you draw a line of best fit, right, you can also see whether, you know what I mean? You can put your ruler like that and see whether, right, there is equal number of points on either side of the line. If you draw a curve, right, you should use a flexi curve or transparent curve ruler with the curve drawing. Something like this will be good. So extrapolation, in physics, you may need to extrapolate, unlike biology. In general, if there's no known relationship between the variables, the line of best fit should not be extrapolated, as a trend line drawn can only describe a relationship within the range of data collected. So in general, right, you don't extrapolate unless the question says so. But as I said, in physics, sometimes they may need you to extrapolate to get a y-intercept, sometimes. But if that is not needed, then there's no need for you to extrapolate your points. So you have your data points, right? You take note of the two extreme points. You should not go beyond that. In plotting your graph, please don't go beyond that. Unless the question requires you to extend the line to find the y-intercept, then that's a different story. Okay, dealing with anonymous results. So this one we mentioned briefly. When a graph is plotted and there are some points that do not follow the general trend or pattern, do not panic. These odd data points are known as anonymous results. If you have enough time, you can repeat to test or verify the reliability. However, if you really do not have time, you're desperate for time, you can still plot this anonymous point, leave it there, and circle anonymous data. This is how I do it. Okay. Yeah. It's important that you do so, and please don't play cheat. Have integrity. Okay, and then these are some of the exemplars and the non-exemplars. Like, for example, I have a student who draw like that. Yeah, I just saw this recently. She drew like that. And it's cross, minus mark. Desirable graph is have a good spread of the graph paper and best fit line. This is a best fit line because the number of points on top and below the graph is about the same. 1 point, 1 point. And you do not need to force it to make them about equal distance. Roughly that will do. Like this one, not bad. 2 points below. But this one, although, because it's a bit hard, this one is like 1 point above, 2 points below. But the thing is, it's still acceptable because, I mean, you won't really, don't waste your time, right, trying to find a fair fit. But like that, even if 1 point above or 2 points below, right, it's also acceptable, okay? So don't waste so much time in trying to get a perfect graph. There's no perfect graph, okay? Because we understand that if we do this on Excel or other software, right, they can do the best fit line very nicely for us. But since we understand that you're doing it manually, right, there will be some discrepancy between the best fit and your so-called best fit. So we accept a range of uncertainty in your answer. So something like this, right, then no choice. This seems to be the best, then we will accept this. Okay. Now, title. This is just an example of a good graph. Yeah. I spent a lot of time on this because a lot of marks are given to table and graph. So it's worthwhile. Yeah, so just some examples. The line, some of the notes to take note for. These are some of the headings, the parts of the graph that you should include, like title, labeling of X and Y axis. Graph size should take out at least 2/3. 3/4. Even better. Choose a suitable skill and ascending order and good skills. Yeah, not odd skills. Using a cross, best fit line. Then this is another example of a good graph. Each axis is labeled with a correct unit. After a slash, only slash. Title, good to have a title. Avoid the use of odd skill. The best fit line, many data, the number of data points on top and below is about the same. A good choice for coordinate, let's say they ask you to find the gradient, right? Try not to choose the raw data that you use, okay, please. Okay, use the points that are not part of the data, okay? Then, I think I talked about that already. Yeah, bold line for easy reading for the axis line. The plotted point should occupy as large portion on the graph paper as possible. Every big square is marked. Okay, graph need not start from 0. Now, for all quantitative data, it should be presented in appropriate number of decimal places or significant figure. So gradient and intercept calculated must always be given to the correct number of significant figure with the correct unit. Okay, now this all, so the gradient, right, may have a unit. Gradient itself by right has no unit, but because if let's say, right, they ask you to fit into the equation, right, then what is the gradient may represent something. So if they ask you, okay, gradient is what, then you say that gradient is the specific value that they want. For example, in this case, right, it could be ohm, which is gradient is a resistance. Then y-intercept also have a unit. So when you represent the gradient and intercept, right, because there is a physical quantity that's associated with a y and x-axis, right? So you better present the gradient with a unit and the intercept with a unit to show what they are. Yeah. So as I said here, gradient and intercept should always show the unit. But gradient itself by right no unit, but when you present it, it should be presented with the unit and correct significant figure or decimal places. So the next part is a planning experiment, which I will go through it as the final portion. The planning experiment in physics is normally part of the question, or it can be a question by itself. So it could be related to the experiment that you've done during your practical exam. So for this part, right, you're expected to identify key variables for a given question, outline experiment procedure, describe how the data is used, and how to identify risk and, if possible, state precaution to minimize the risk. So here are some basic guidelines to consider when planning the experiment. Do pay attention to the requirement also in the question. So if a question asks you to do this, you better fulfill the requirements, okay, to score the point. When an equation is provided in the question, it is always best to linearize the equation in the form of y equals ms plus c. So whatever equation they give you, if you can, linearize it so that you can identify what is the dependent variable and independent variable. Okay, so from the equation, you identify what is the independent variable they are trying to control and change, and how to measure it. And then you proceed to identify the dependent variable. The dependent variable is the variable that depends on the independent variable and will undergo a change whenever you change the independent variable. For example, an experiment may involve adjusting the length of the spring by changing the experiment may involve you adding different weight to the spring to extend the spring. So the weight that you add to the spring is the independent variable because that is the quantity that you are controlling and you are changing at regular interval. But by doing so, the length of the spring changes. So the length of the spring, or should I say the extension of the spring, will become the dependent variable. And you are supposed to measure that as well. So you must be able to identify what is the independent variable and dependent variable as shown in the equation. When the dependent variable is a quantity that cannot be measured directly from the experiment, for example, period, they want you to find period, then you need to state how to get the period, how to get the derived quantity. So for example, for determining the period of oscillation, you can say it can be derived from the measured quantity by taking the time and take the repeat and get the second time and take the average and then divide by 20 to get the period. Okay, so you need to mention that in your procedure. That is part of the points to consider. And state how to vary the independent variable. How do you adjust the thing? Okay, the variable that you need to change. And of course, you need to mention the control variable. What are the variables that you're keeping constant? So the variable part is very important. What is the independent variable? What is the dependent variable? How do you measure them? And what is the control variable? And how do you keep that constant throughout the experiment? All right. Repeat the experiment 5 further times. So if it's a straight line, it's about at least 6 points. If it's a curve, at least 8 points. Okay, you did not need to carry out the experiment. You just plan and write it down so that the experimental who see the procedure will know how to proceed with it. So the instruction has to be clear, concise, to the point. Okay, describe how you manipulate the data to verify your investigation. So you can actually present the form of graph, or it can be other forms like charts or tables. And then maybe you say plot a graph of y against x and then determine the gradient. Then the gradient will represent what? Something like that. Okay, draw conclusion from results to verify your investigation. For example, if the graph is a straight line, then the quantities plotted are linearly related. In cases when an equation is provided, you may need to state how to determine the constant. For example, you may want to inform the experimental after she or he finish plotting the graph, remind them the need to obtain the gradient and the y-intercept so that to get the constant from the graph or constant from the equation and to solve the question. If there's any safety precaution, please state them. That could be a marking point. Okay. If the planning is considered to be relatively safe, then there's no need to state precaution. Okay, so it's important that you must write down the suggestion to improve reliability. Like you cannot just do one set and that's it. You may want to repeat, especially if it involves time where it's highly inaccurate. So taking more readings and average is improving the reliability. Okay, so a possible template which I also provide to answering planning questions is something like this. the text in the square bracket is what you expected to do, by the way. So the independent variable, dependent variable, and control or constant variable must be mentioned in your procedure. You may need to draw a diagram when needed. Okay, set up the apparatus as shown. However, if this planning question is linked to your experiment, then you are lucky. You can just say set an apparatus as shown in figure what. Then you are safe. But sometimes this planning question may be an isolated question. Then you have to draw. For example, finding out how different weight affect the extension of the spring. Then you have to draw. If that say this is a separate one from what was given in the question. Okay. Set up the independent variable to a certain value by using apparatus or steps. List the step to measure and record the reading of dependent variable or reading that could lead to dependent variable using apparatus. So you need to mention the apparatus that you are using. You cannot just say measure the length using what, measure the volume of liquid using what, or something like you need to be specific in the apparatus that you will use to measure the dependent variable or the independent variable. Keep the control variable constant, measure and record readings. Get at least 5 other values for straight line, but for curve, I already said 8 points. So for curve, for straight line total, for straight line, 6 point minimum. Okay. For curve, must be more than 6 lah. It has to be about 8 points. So you do one reading, you get 5 other points. For curve, you do one reading, get another 7 points. List the step needed to convert the measured value to dependent variable required. Plot a graph. Very standard procedure, because for all physics practical, right, very likely it's about plotting graph most of the time based on past year paper. Draw conclusion and then safety precaution if that is. So I have also listed out the 10-step approach to planning, which may be helpful. Like number 1, look at the equation they give you and see what are the constant. Highlight the constant. The non-highlighted one, for example, you have a value like this. I can't think of the equation now, but it's something like it look like in the format of y equal mx plus c. So when you look at this, right, you highlight the constant m and c. This one will be the non-highlighted quantity. So this will be the dependent variable that you are measuring whenever you change the independent variable x here. Okay, then you plot a graph, compare, and state how you use the graph to determine the unknown. So this is step 7. So 1, 2, 3, 4, 5, 6, 7. Step 8, discuss key variables to keep constant. Safety precaution, if there's any. This one is optional, okay? Then we go to number 10, procedure. Then you can start writing your procedure. You can take first part of an experiment if it's an extension. Preparation stage, measure, record, instrument, initial value, keeping key variable constant, repeat at least 6 steps for straight line, wide range, blah, blah, blah. Okay, so at the end of this video, right, I will just show you a past year question from 2017. How a planning question looks like and the marking scheme for this particular question. Okay, I have a few samples, but I only have time to go through one of them. Again, if you're interested, you can get a copy from me where I will have you have access to all the different types of questions. Okay, so this experiment is about the student investigating how the material of a spring affects its behavior when stretched. So these are the materials available, wires of different thickness, length, material. Set of 10-gram masses and a set of 100-gram masses with hangers so that you can hang them on the spring to extend the spring using different masses. And you have a wooden rod about 1 cm in diameter and other standard lab equipment like electronic balance, retort stand, etc. plan experiment to enable you to test the stretch of spring made from different materials. You don't need to carry out as a plan experiment. So in your plan, you should include instruction. How do you make the spring from the wire? So you must twist the wire to make into a spring, right? And what will you measure? The instructions, the variables to ensure the comparison of fair test, meaning the control variables or the constant variables, any precaution, and how you present your data. If you need to, you can draw a diagram. This is optional, but but with a diagram, it can shorten your procedure because picture speaks 1,000 words. So if you can draw, it will be very helpful so that it helps the experimental to visualize and able to set up. I mean, whenever your teacher gave a practical question, there'll be a diagram for you to follow. So you know how to set up, right? But if the diagram is not given, it's harder. Now, so the marking points, this is not in complete sentences, but these are the points that we look out for. For example, you must mention about the spring is how is it made. Very briefly, just say that you wind the wire around the rod because they give you a rod, right? So how do you make into a spring? So you put this is the rod, right? So you can say the wire, you can wind it to make into a spring, something like that. Okay, something like that. So you wind it around the rod and make into a spring that's coiled up. The method you can apply the load, measure the length or extension of the spring, repeat the spring for different material, and record the result in suitable annotated table, bar chart, or graph. So you can just present on a table to show the effect of having different material on the extension of the spring. So you can add the load using the hanger on the spring and then measure the extension of the spring. Then you repeat that procedure with other material. The control variable, so throughout the experiment, the original length of spring will be constant. Diameter of wire is assumed to be constant. The coil spacing or the load, the range of load used, and the diameter of the spring as well. Any precautions or difficulty, any two of it will do, like while clamping the retort stand might topple. So try to use small loads. The spring might experience overstretch and it may be so overstretched that it cannot be able to support any load. So try not to use too heavy loads, like 100 grams. I mean, many 100 grams one go. I mean, you don't do that. So you use small load at the start to prevent overstretch. And then apply the force smoothly, slowly, suggested range of loads. Workable arrangement for applying load to spring. For example, you may have a small loop at the end of spring to help you hook up the load. Try experiment to find the range of load. So to prevent the spring from over. So the whole difficulty is about you scared the spring will overstretch. So you try to experiment first to find how much you can go. Okay, and of course, also need to mention how you determine the extension by placing your ruler, but the ruler may not be straightened. So you must make sure that you must use a set square to make sure that the ruler is perpendicular to the ground so that an accurate vertical extension of the spring is accurately measured, all these things, okay? So you may have to maybe draw a diagram to show the spring and then have the ruler at the side of it so that you can measure the extension accurately. And make sure that the ruler, with the help of a set square, is held perpendicular, okay? Yeah, to the spring. The spring also must be vertical. So you also need to make sure that the clamp on the retort stand, right, that hold the spring, right, is in perpendicular orientation. It is 90 degrees to the retort stand, something like that. Take at least 5 readings if you produce a graph. Okay, so that's about it. So I hope you benefited from here. So any question, feel free to ask me. Thank you.